G'day viewers. In this segment I'll talk about IP version 6, the future of the Internet Protocol. So most of us use IPv4 when we access the Internet today, IP version 4 that is. But there's a new version of the Internet Protocol, IP version 6, which has been standardized and has been deployed into the Internet to solve some problems. I should say maybe that it's still being deployed because it's been in the process of being deployed for more than a decade now. So in this segment I'm going to talk about why we need IPv6, what it is, and what the state of it is, how it's been rolled out. Okay, so here's the background. This is a slide, actually you saw this slide earlier on in I think the first week of the course. This slide simply shows you the graph, gives you the internet growth, and you can see how rapidly the internet is growing. Excuse me. It's really exponential growth here as we trend up the line. And over the past couple of decades, we've gone from, a small number of million hosts to 1 billion. This is a huge number of hosts on the internet and still growing rapidly as every device goes online. And to top it all off, we're using 32-bit addresses. With 32-bit addresses, we have a maximum of 2 to the 32 addresses. That's basically about 4 billion. Actually, there are fewer addresses because there are all sorts of reserved things and format difficulties and so forth. So there are many fewer than 4 billion addresses. Not only that, but you can't use them all because we allocate these addresses in blocks. So we've used up a good fraction of the internet's usable addresses already. Actually, the situation is more dire than I'm letting on. We are very close to the end of the availability of new IPv4 addresses. This somewhat complicated diagram on the left shows how IP addresses are allocated. IP addresses start with a body called IANA, the Internet Assigned Number Authority, I think. And IANA owns all of the IP space. What IANA does is it hands it out, big chunk at a time, to these other bodies which are shown here. These are the arrows going here. These other bodies, ARIN, APNIC, RIPE, LACNIC, and AFRINIC, you might have heard of or you might not. These are regional bodies that hand out, that administer IP addresses in different parts of the world. ARIN is for the US, Canada, and various other bits of the world. I think Antarctica, for instance. RIPE covers most of Europe, and you can see all of the other bodies for Latin America, Africa, and the Asia Pacific region. APNIC covers Australia, of course. So IANA hands off IP addresses to all of these bodies, and these bodies in turn hand out IP addresses to ISPs and other companies when they ask for them. Now, IANA has handed out all of its IP addresses. It exhausted the addresses in February of 2011. So that's a little while ago. That's almost a couple of years ago now. You might think this is no big deal, but IANA has been going for, I think, more than 40 years handing out IP addresses, and just in recent history, it's run out. So this means the routing registries really have only their leftover blocks to use. Already, some of the routing registries have run out. RIPE, it's the other way around. APNIC was the first to go. In April of 2011, it ran out. Much more recently, RIPE ran out of addresses in September of last year. So everyone is sort of on a countdown. Now that the addresses are almost gone, much tighter allocation policies have been used. You need to satisfy many greater hurdles if you are to obtain new IP addresses. And secondary markets are springing up where companies are selling the IP addresses they already have to other companies and so forth. So it's all getting more difficult. Maybe this is actually somehow tied to the end of the world, the Mayan calendar. At the end of 2012, the world's going to end because we run out of IP addresses. What can we do? Well, don't worry, don't panic. This will be, one of those softs falling off the cliff kind of things. And there's a solution in the wings. It's IP version 6 is going to come to our rescue. Actually, it's been coming to our rescue for a very long time already now. IP version 6 was an effort started almost 20 years ago by the ATF in 1994, following on some research. The main feature of it really is motivated by this addressing crisis. The exhaustion of addresses is much larger addresses. These addresses are 128 bits long, And 2 to the 128th power is an enormous number. It's not simply 4 times as big as 2 to the 32, it's 2 to the 96 times as big. So there are more addresses than essentially every device on the planet in the foreseeable future in this number, many more. It's an astronomical number. The reason for starting on IP version 6 with these big addresses, even almost 20 years ago, was that the growth of the internet was obvious then, and it was clear that we would shoot through these addresses. And really, different techniques people have been using have only been delaying the end of these addresses. IP version 6 also includes many sundry small improvements. Basically, you really don't get to change the internet protocol, the bedrock of the internet, very often at all. It's a very rare event, so everyone would like to take advantage of it to clean up a few things in many ways. IP version 6, by the way, is the version that comes after IP version 4. 5 was allocated to a protocol that never really made it big time, so it's disappeared. At any rate, IP version 6 became a standard in 1998. That's more than a decade ago. So what's happened? Since it became a standard, after that, it was expected that people would begin to deploy it. Well, really very little's happened in the past decade. Maybe that's not quite fair. There's been various improvements. Windows notably began to ship it around 2000. Other major operating systems had begun to ship it and had it enabled by about 2008. So all sorts of people got a little ready in the meantime. But I think the big point is here. Deployment has really been hampered, greatly hampered by the difficulty of deploying it. We'll talk about that in a while, because it's really such a big change to the internet. And also a lack of adoption incentives. I mean, if you're a new ISP or company, why should you bother installing IPv6 if you can still get IPv4 addresses? It gives you a lot of headache and not really a lot of new features. So deployment has been very slow. Of course, now, in recent history, over the past couple of years, there's a big push to deploy IPv6, and it's beginning to take off because the exhaustion of IP addresses is really very close, and so the price of IP addresses will shoot up, and the costs and the difficulties, and we'll gradually switch over to IPv6. This slide shows you a little bit about IPv6 deployment. The medal here is a campaign to launch into the future with IPv6. It's World IPv6 Launch Day, and that was about the middle of 2012. It follows about a year after a World IPv6 Day in which ISPs and many large networks turned on IPv6 for a day just to try and do a bit of a test and debug it, since it is such a big change to the internet. They wanted to see if everything's compatible. That went well enough that in World IPv6 Launch Day, many big content providers and ISPs turned on IPv6 and left it on so that you can now begin to use it. This graph comes from Google. It shows you just some of their data that you can look up of how many of their different users are coming to them and making queries using IPv6 rather than IPv4. You can see a while ago it started at basically nothing, and it's been going up, and I think we're getting ready for some growth, at least I hope. Here, in case you can't read it easily, this is about 1% of the traffic, so IPv6 is still very much in the noise. But hopefully it's growing very rapidly now. So I still haven't really told you what IPv6 is. What we're going to do now is just look at the header of IPv6 so we can see the messages and just see what's a little bit different compared to all of the IPv4 messages. So here's another one of those header diagrams. It looks maybe the same sort of thing as IPv4, but it is different in some respects. The biggest difference by far is this shaded region. These are the addresses, the source and destination addresses. They now take up the bulk of the header because they're huge. They're 4 times bigger than the IP addresses used to be before them. So because of that, we have a new convention for how to write them. IPv6 addresses are written as 8 groups of 4 hexadecimal digits. Each of these 4 hexadecimal digits really corresponds to 16 bits. That's why there are 8 of them to make 128 bits. So here's an example in longhand notation of an IPv6 address. You see this address here, 2001:0 DB8:0000, another zeros, FF00, 0042, 8329, and so on. Wow, that's a very long address. Most of the notation we use is about how to shorten those addresses so that we don't have to write it in such a longhand way. There are two rules for shortening essentially. You're allowed to, within a group of 4, omit the leading zeros, and you're also allowed to omit entirely groups of zeros. We'll know the range of ones which have been omitted by, usually there's just one run of them, by seeing that there are 2 colons in a row. So let me just write out, and you can help me, what this address would be in the new notation. So I'm going to shorten each group as I go across. So 2001, colon, I'm going to get rid of this 0, DB8, colon. Oh, look, I can get rid of this block, and this block. Now I'm left with another colon there. Then I've got FF00. I can't get rid of these 0 zeros because they mean something at the end. It would be a different number otherwise. Colon, get rid of this. 42, colon, 8329. Well, that's still pretty long, but it's a lot shorter than what we started with. So those are the addresses. What else is in the header? Well, there are lots of other smaller changes. I've shaded the other header fields. One feature of IPv6 is a more streamlined header processing. If you want to, you can compare it to IPv4 and you can read more about it in your text just to understand some of these details in more detail than I'm going to give you. You might notice, for instance, that the header length field has disappeared. The header has a fixed length here, and the next header points towards anything that's optional as well as the higher layer headers. You can also see that the header checksum has disappeared. That was something that maybe added a little bit of reliability, but it wasn't felt to be worth it and the complications in practice. So things have gotten simpler here. There's also a feature called a flow label that's likely to be important in the future. Recall that datagrams are all sent individually through routers, but often if we're doing something, all of these datagrams might belong to a higher level construct, like a video conference. What you can do is use this flow label to put labels on packets and identify the ones which are in the same group together. This is almost a little like a virtual circuit, just without any of the setup. If we do this, then we almost have a basis for the network to treat all packets with the same flow label in the same way. It might route them the same way through the network, forward them the same way through the network, Or it might try and do different things in terms of congestion or priority with them in the same way. This is mostly in the future, and this is to do with quality of service. We'll probably get to that later. And finally, IPv6 has a better fit with some of these advanced features. Now, I'm not going to go into all of the details here. The point I would just make is that over time, lots of experience has been gained in the internet with how to implement mobility, different kinds of multicasting. That's sort of like a cross between unicast and broadcast, so a packet is sent to a group, and a little bit extra security. Those learnings have been incorporated into IP just to sort of make the fit between these features and IP a little smoother. So this is basically what IPv6 looks like. Now let's talk about the big issue for IPv6, and that's the transition. If IPv6 is such a big thing and we really need it, great, let's get on with it. But how do we go about using it? How do we transition to it? The internet is far too big for us to have any kind of flag day where we say, everyone stop using IPv4 and start using IPv6. Instead, both of the protocols will need to coexist, probably for decades together. So we need some deployment strategy which will let us deploy IPv6 and begin to allow people on IPv6 networks to talk amongst themselves and with people on IPv4 networks. This is very difficult. It's really an internetworking problem, like before, but it's difficult because there are fundamental incompatibilities. They have very different addresses, for instance. How on earth are we ever going to get them to talk directly to one another? Well, this is the problem, and there's no magic answer here. In fact, dozens of different approaches have been proposed. I can't go into them all. That would be more detailed than we want. But I can just sketch some of the different alternatives, and I'll go into one in detail because it's useful. So some people have proposed running what's called a dual stack. If you have a host, you might have it speak both IPv4 and IPv6. That way, it could use the old IPv4 protocol to communicate to old hosts, which are on an IPv4 network, And it could use the new IPv6 protocol to communicate with IPv6 hosts on a new IPv6 network. Another approach is to add translators into the network and try and convert packets from one to the other. That will allow us to talk across IPv6 and IPv4 hosts. It'd be wonderful if we could do it. It's just kind of hard, and there are various constraints because, for instance, we have to work out how to fit IPv4 and IPv6 addresses in each other's packets using some kind of convention. And the third approach is something called tunnels. We might have islands of IPv6 where new networks which are using IPv6 are set up, but they might not all be connected. Some of them might be connected via the IPv4 network. We can tunnel across the IPv4 network to allow the IPv6 hosts to talk with one another. And this is the one that I'm going to explain in a slide or so, just so you can get the sense of how tunnels work. Here really to help with IPv6, but tunnels are a useful mechanism in general. They're not specific to IPv6. So here is the tunneling scenario. We have on the left, we have an IPv6 network. On the right, we have another IPv6 network. So we'd like to send a packet from the source on to the destination. Source on the left, destination on the right. They're both on IPv6 networks. Sounds wonderful, except of course in the middle, we have an IPv4 network. Now, because these are very different protocols, what we probably can't do, for instance, is have a host in this IPv6 network talk directly to a host in this IPv4 network. They speak different protocols. So we're not even going to try. We really just want to get our source to communicate with our destination, even though the path goes across an IPv4 network. What can we do? Well, here's what we can do. We can send our IPv6 packet, because that's what will be produced by the source, across the network, the IPv6 network. Then it will get to the border router, which is at the edge of an IPv4 network. At that time, what we can do is simply wrap the IPv6 packet in an IPv4 packet. We'll take it as a payload and not even look at the IPv6 packet. We'll simply encapsulate it with our own IPv4 packet and send it to another border router on the other side of the network so that it can get back onto an IPv6 network. This is a tunnel in the middle here. And it's called a tunnel because when the packet goes into it with this wrapper, this IPv4 wrapper, it's going to come out the other side. It can't get out halfway through the tunnel and go to, say, this host up here. It has to go through the network. So it can only go through this tunnel and out the other side. Now, in fact, if we look at the source and destination of this IPv4, we'll have the source will be here, this ingress router, and the destination will be here. It's identifying the tunnel endpoints, and the wrapper is just to carry the IPv6 packet through there. Once it gets to the other side, it can be unwrapped, and then it will go across the IPv6 network and arrive at the destination. So effectively, this IPv4 network in the middle is acting as a single logical link. That's how we're folding it into our network. Let's try and draw some of the layered protocol stacks for that, just to make sure we understand it. So on the sender side, let's say we have IPv6 on top of some link protocol, such as Ethernet. So we're going to have the same thing on the receiver side, IPv6 link. In the middle, what's going to happen? Well, at this ingress, we need to have the same thing. Sorry, this is meant to go here, IPv6 and link, because we need to terminate these protocols. But now we need to enter the tunnel. So we're actually going to do something tricky on this side. We'll have IPv6. We need to have this because we are maintaining IPv6 connectivity across this entire path. But underneath IPv6, we'll put IPv4. That means we will take an IPv6 packet and encapsulate it in an IPv4 packet. And then the link layer. And so we've got to do the reverse on the other side. So I'll have to have 3 in here. And this then will be our tunnel over IPv4. Whereas this is really a native IPv6 network, and so is this. So that's what the protocol layers will look like corresponding to those packet formats. You can see this is a bit of a strange device. We're putting a network layer on top of a network layer just to provide a fancy path. But it's quite effective. And tunneling, we'll see it again in some other contexts when we get to security and look at VPNs, for instance. Here's the diagram. Again, just cleaned up so you can see. Yep, and check that I got it right and check your understanding. But that's basically it. Now you know about tunneling, you know about IPv6, and at least one option for how it can be rolled out.